Okay, our last lecture for Chapter 3 comes from Section 3.9 called Step Functions. Now, you have probably seen these graphs before, but I'm not sure you were ever calculating with them, so this will be new information. So pay attention, and you may have several questions that you'll come to class with. Evaluate expressions based on step functions. We want to model different situations that lead to step functions, and graph and interpret graphs that are actually step functions. Now, in order to start this, we need to discuss a new symbol. Take a look. This looks a lot like our absolute value function, some people will say. They'll also say it looks a lot like our bracket function, so be careful. Here's absolute value of x. Here's just a bracket of x. This is different in that it has the bottom piece of the bracket only, no top piece of the bracket. And you can sort of see why if you look at the names. It's called a greatest integer function, it's called the rounding down function, or it's called the floor function. Those last two names really help out because rounding down, the only place you have a extra piece from your absolute value bars is in the down or lower portion. The floor function, think of it, we are like drawing the floor. We are drawing the bottom part of this cylinder, of this room, whatever you want to call it, but we only have the down bracket. So if we have the down pieces, the definition says the greatest integer function is the greatest integer less than or equal to x. And x is whatever you're evaluating inside those brackets. So if we look at our examples here, and notice we have what is the greatest integer function of 3.6. So your brain has to say that means I need to take and round down the number 3.6 to the greatest integer less than or equal to it. So less than or equal to 3.6, we would be looking at the number 3. Rounding down function on a whole number is just that number itself. There is nothing to round. On a negative number, whole, it's just the number itself. Now be careful on the next two. On a negative number that's whole, or that's not whole, use the definition. I want the greatest integer less than or equal to x. And keep in mind that you're in the negatives. So if we're down here between -3 and -2 right now, and we're heading in the positive direction, and we know the positive direction is the greater direction, then we have to employ that into our thinking. So -2.3 rounding down function would be a -2. It's the greatest integer. Look at -12.9. So now think, if you're down here, out here between -13 and -12, you're out here about at 12.9, and it's negative. Greatest integer less than or equal to that number would not be -13, which you're used to doing with normal rounding. It would be -12, because -12 is actually closer to greater than the -13. So it's a rounding down function. Think of it that. And down in the negatives has to take us to the greater value. Questions there? If you have any, or you're not sure what's going to happen inside those brackets, it does create a little problem when we go and look at a graph with that kind of feature in it, the greatest integer function. Now, this is what it might look like in a equation or a function setup. If g of x is actually the rule, 2 plus the greatest integer function of x, and it says evaluate, then they're saying g of 2.6. So your job is to take 2.6, wherever there is an x in your function is where you put that in. So your brain is really saying g of 2.6 is 2 plus the greatest integer function of that 2.6. And greatest integer function of 2.6 is 2. 2 plus 2 is 4. So when we do the math there, we get a final answer of 4. Greatest integer function of a negative 3.1. Remember, we're going greater. So we would get a negative 3 in this case when we put it into the function. So 2 plus the greatest integer function of negative 3.1. That alone gives me the negative 3, because you think, what is it between? It's between negative 3 and negative 4. Which one's the greater number? Negative 3 is. Negative 3 plus 2 is negative 1. And then we've got g of pi. Think of your value. G is pi, 3.14159. So it's a decimal. So here we go. We'd have 2 plus the greatest integer function of pi. And if you want to put 3.14, and start thinking of it that way. Greatest integer function of 3.14 would be a 3. 3 plus 2 is 5. So our final answer there would be a 5. So this would be an example of evaluating functions that have the greatest integer function in it. So now let's go to where I said there's going to be a slight issue, and that would be with our graphs. If we were to graph or asked to graph a function that had an equation with the greatest integer function in it, we're going to have to make sure we definitely evaluate our usual positive and negative whole numbers. And then right along with that, we've snuck in easy decimals that fall between those whole numbers. And that will be key as we look at our numbers. Okay? So everybody make your XY table. Remember, f of x is nothing more than our y, our result, our outcome. So if we were trying to graph that, and I will be showing you in class what we need to do with our calculator, with technology, to get a greatest integer function on our calculator. We can do that, but the graph is going to be a little tricky, so we need to be able to do them by hand as well. Okay, so let's set up, and right now I think we can set up our graph as 1, so we'll assume our graph is by 1s. Let's do as we usually do. The XY table has to be calculated first. We can see up here that our rule is take the greatest integer function of x and then subtract 1. So if we put a negative 2, greatest integer function would stay negative 2. Negative 2 minus 1 is negative 3. Let's do the next whole number, because the whole numbers are the easier ones. Do negative 1. Greatest integer function of negative 1 is negative 1. Subtract 1 is negative 2. 0. Greatest integer function of 0 is 0. Subtract 1 is negative 1. Greatest integer function of 1 is 1. 1 minus 1 is 0. Greatest integer function of 2 is 2. 2 minus 1 is 1. So we have all the whole numbers, which is easy. You could graph points, but that's the problem. On a greatest integer function, it's all the decimal values that would be crucial. So I've picked nice, easy decimals that fall in between all your whole numbers. You can pick the harder ones, but you got to remember, no matter what I pick, and we'll do that right now, no matter what I pick here, I'm between negative 1 and negative 2. Even if I pick negative 1.1, all the way up to negative 1.9. Whoops, sorry, all the way up to, that's an arrow. Those numbers all would go in the rounding down function. And think about it. If this was a negative, if your rounding down value was a negative 1.1, it would go to a negative 1. A negative 1.2 goes to a negative 1. A negative 1.3, 1.4, 1.5, 6, 7, 8. Negative 1.9. Greatest integer function says round down, it goes to a negative 1. So even our negative 1.5 goes down to a negative 1. So if all of these numbers go to a negative 1, and then we subtract 1 from it, they're going to end up with the same value that that whole number, negative 1, did. Interesting. Go again. Now we're thinking of all the numbers between 0 and negative 1, all the decimals. Think of all that. All the decimals that fall between 0 and negative 1. And we're just doing one of them, a negative 0.5. So you could do a negative 0.9 all the way down to a negative 0.1. Or even if you want to go smaller, negative 0.0000001. All those decimals would, with a grounding down function, go to 0. And then 0 subtract 1 is negative 1. So all those decimals that fall between 0 and negative 1 have the same value that the 0 did. Keep going. If we have a 0.5, and again, this would be the same as give me all the numbers between 0 through 1, all the whole numbers, 0 through 1. And we're just picking one of them out because they all have the same thing. So a 0.1, 2, 3, 4, 5, 6, 7, 8, 9 all have the same result because they all get rounded down. A 0.5 rounds down to a 0. Sorry, a 0.5 greatest integer function rounds down to a 0. And so that 0.5 becomes a 0, and a 0 take away 1 is negative 1. And we do have a problem. What did I screw up on? I'm at any number between, so a 0.9 would go down to a 0. Greatest integer function less than or equal to. So when I went to everything between okay, if you notice the mistake was where he said rounding down function, and we actually went up on a couple of them. So let's go back. We've got all the whole numbers in there, and so that shouldn't be a problem. Now, if we go back and we look at negative 1.1 to negative 1.9, when we say where is that going to go, a negative 1.5 rounds down to a negative 2. And a negative 2 subtract 1 is a negative 3. Go to the negative 0.5. If we're at negative a half and we round down, that's a negative 1. Rounding down and then subtract 1 is a negative 2. And go back to the 0.5 where I caught the mistake. Says we're at 0.5. Rounding down function would put us at 0. 0 subtract 1 gives us a negative 1. Now we're at 1.5, and rounding down function would put us at 1. And 1 minus 1 is 0. All right, so with the error corrected, you will know you have a sequence of numbers that all fall in a pattern. When I say in a pattern, we've got a whole set of numbers right there to there that come out to negative 3. Another set from here to here that come out to negative 2. Same thing here. So we have an interval of numbers that come out. And once we establish those intervals on our graph, that's where the steps will come from. That's where our intervals will show up, and you will see that stair-step graph. All right, so let's be very careful when we graph this time and not make the same kind of mistake, Mrs. Morris. We want all the x values, remember, between negative 1 and negative 2. So go to your graph. All the x values, negative 1 to negative 2, fall right in this position. but we need to be down at a y value of -3. So follow that down to -3. So you're between -1 and -2. Now notice, if we went and graphed all of these, you could graph the whole numbers first. That's easiest. If you go -2 and you know -2 is at -3, you know that for sure. So there's -2, -3. And if you graph the whole number, -1, -2. And if you graph the whole number 0, -1, you can see you have a nice linear situation, but it's not going to be a line that you draw and connect. We're at 1 and 0. And then the last one, we're at 2 and 1. If you graph all the whole numbers first, you're on your way to making your steps. So now go back. All the numbers between, and this is what you're looking at, all the x values between -1, but not including -1, and -2. So all the x values between -1, not including -1, means open circle at -1, and all the way to -2. So here's all those x values right in here. Make it nice and dark, and they're at -3. Then go to the next intervals. We want all of our decimals between 0 and -1. So 0 and -1 is going to give us a y value of -2. So 0 is an open circle. All the decimals between 0 and -1 give us a y value at -2. So you can start to see our steps forming. Next group. We need all the values between 0 and 1. 1 is not included, so it's an open circle at 1, but all those decimals between 0 and 1. And we keep going, and once we have the pattern established, we can just keep drawing. We don't even have to look at our table at that point. Open circle, everything left. We could draw another one here, open circle, closed circle, everything. So they might say on the graph, you know, for the first X number of integers, they might just say till you have the pattern. But notice, open circle in this case is on the right, and closed circles on the left. That will stay. You will not be jumping around and the circles changing. So there's a pattern to it. There is a step, and if you just think we're going up the steps in our graph, you can see that very easily. They're sort of like suspended in thin air, nothing holding them up. That would be an example of our step graph. So what you saw there, quick review, is that it is important to graph the whole numbers as we always have, but probably even more important are making sure you check out these intervals. All decimals that fall in between these whole numbers are key. And if you don't evaluate those correctly, you may end up with a mistake like we did in the beginning, and or you will have dots, and those dots should not be true. So this is where we say we now have a step function graph. And our greatest integer function is a key piece. Anytime you see that, you should be thinking step function graph. Now, out in the real world, where would step functions really occur? A lot of them take place in places where you can have a range of things happening. Like if you've ever gone and mailed a package, you might have anything between 2 to 3 pounds gets this cost. Each pound you go up has a common price. Same thing when you mail a letter or a smaller package. Parking garage fees are usually pretty typical. They're by the hour. So if you're there for 1 hour and 2 minutes, you're paying the same price as if you're there for 1 hour and 58 minutes. So it's those kind of situations in the real world that you will be graphing or asked to analyze based on the idea of step functions. So I think we're good to go. Bring all your questions and examples or questions about graphs to class.